Interstellar comets are rare. That is what astronomers told us. In over a century of watching the skies, humanity detected only 2 confirmed visitors from beyond the solar system. Oumuamua in 2017, then 2I Borisov in 2019. These were objects from another star system, drifting for millions or billions of years through the void. But on July 1st, 2025, telescopes in Chile locked onto something that shattered every assumption we had about interstellar visitors. It was wrong. The rarity, the expectations, the mathematical models, all of it collapsed when scientists calculated the velocity. This object was moving at 210,000 kilometers per hour, the fastest speed ever recorded for a solar system visitor. It was also the largest, the most active, and potentially the oldest cosmic body any ever observed from interstellar space. The stakes are staggering. If this comet were on a collision course with Earth, we would face an extinction-level catastrophe with technology wholly inadequate to stop it. If you want to discover what happens when an interstellar comet barrels toward our planet, hit that like button and subscribe. Brace yourselves. The revelation begins. The object is designated 3I Sal Atlas. The 3I means third interstellar object. The Atlas refers to the Asteroid Terrestrial Impact Last Alert System, a NASA-funded network of telescopes designed to detect objects that could threaten Earth. When the telescope in Rio Hurtado, Chile, flagged this object, astronomers immediately recognized something impossible. The trajectory was hyperbolic. That is the mathematical signature of an unbound orbit. It does not loop around the Sun like planets, asteroids, or comets born in our solar system. It came from somewhere else. When scientists traced its path backward through space, they confirmed the origin. Interstellar space, the vast darkness between stars. But 3I Atlas is not just another rock. It is a comet, an active one, spewing gas and dust as it races through the solar system. Observations from the Hubble Space Telescope captured a dust plume erupting from its sun-warmed side and the faint whisper of a tail streaming behind it. The James Webb Space Telescope analyzed its coma, the glowing halo of gas surrounding the nucleus, and detected carbon dioxide, water vapor, carbon monoxide, carbonyl sulfide, and water ice. This chemical signature is a record, a frozen archive of another star system. Every molecule escaping from 3I Atlas carries information about a planetary disk that existed billions of years ago, light years away. The size remains uncertain. Estimates range from a few hundred meters to a few kilometers across. What is certain is the speed. When discovered, 3I Atlas was traveling at roughly 61 kilometers per second. As it falls toward the Sun, gravity accelerates it further. At perihelion, the closest point to the Sun, on October 29, 2025, it will reach 68 kilometers per second. For perspective, that is over 150,000 miles per hour. At that velocity, the comet could cross the distance from Earth to the Moon in less than 2 hours. The math is brutal. And then there is the age. Scientists analyzed the comet's velocity components in the galactic coordinate system. They broke down its motion into 3 vectors: movement away from the galactic center, transverse motion, and vertical motion through the galactic plane. The vertical velocity component is unusually high compared to nearby stars and other interstellar objects. This means 3I Atlas follows a tilted orbit around the Milky Way and likely belongs to the thick disk population. The thick disk consists of older stars with lower levels of heavy elements than the Sun. Based on the typical ages of stars in that region, researchers estimate with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old. The solar system is 4.6 billion years old. This comet may predate the Sun, the Earth, the formation of everything we call home. It is a time capsule from the primordial Milky Way. The discovery site matters. Atlas detected 3I Atlas while it was 410 million miles from the Sun, within the orbit of Jupiter. The comet was approaching from the direction of Sagittarius, the constellation that hosts the central region of the Milky Way. It had been drifting for millions or billions of years, invisible, undetected, a ghost traveling through the void. Only when it crossed into the inner solar system did the Sun's heat awaken it. The frozen nucleus began to sublimate, transforming solid ice into vapor and releasing dust into space. That activity made it visible. Without the Sun's energy, 3I Atlas would have passed through unnoticed. The object is massive by interstellar standards. It dwarfs Oumuamua, which was estimated at just a few hundred meters long. Early analysis suggests 3I Atlas could be several kilometers across, though uncertainties remain. What shocks astronomers is the water production rate. Observations from NASA's Neil Gehrels Swift Observatory detected hydroxyl OH emission near 3085 angstroms in August 2025. This revealed that 3I Atlas was releasing water vapor at a rate of approximately 40 kilograms per second. That is 88 pounds every second. At a heliocentric distance of 2.9 astronomical units, nearly 3 times the distance from Earth to the Sun, water sublimation should be inefficient. Yet 3I Atlas was spewing water like a cosmic fire hydrant. The inferred production rate implies an active surface area of at least 7.8 square kilometers. If the comet's diameter is around 2.8 kilometers, that means over 8% of its surface is actively outgassing. Most solar system comets show far less activity. The science screamed. There is another anomaly. The coma of 3I Atlas has a carbon dioxide to water mixing ratio of 8.0 plus or minus 1.0. This is one of the highest CO2 abundances ever seen in a comet, especially at its distance from the Sun, when first observed by JWST. Solar system comets generally follow a predictable trend. CO2 to water ratios increase with distance from the Sun because carbon dioxide sublimates more readily than water at greater distances. Only 3I Atlas and the bizarre Oort cloud comet, C2016 R2 Pan-STARRS, break this rule. Scientists do not know why. One hypothesis suggests 3I Atlas has a CO2-rich nucleus, possibly because it formed near the carbon dioxide frost line in its parent star's protoplanetary disk, or was exposed to extreme radiation. Alternatively, the comet might have an unusually thick, insulating crust, hiding vast reserves of water ice beneath the surface. The mystery remains unsolved. The trajectory of 3I Atlas is a cosmic coincidence. Its orbital plane is tilted 175 degrees with respect to the ecliptic, the plane in which Earth and other planets orbit the Sun. This means the comet is traveling in a retrograde direction, moving backward relative to the planets, but inclined only 5 degrees. It almost perfectly aligns with the solar system's orbital plane. This alignment is pure chance. The path will bring 3I Atlas close to Venus, Mars, and Jupiter, but not Earth. On October 3rd, 2025, it passed Mars at a distance of 0.19 astronomical units, roughly 28 million kilometers. ESA's Mars Express, an ExoMars trace gas orbiter, observed the comet during this close approach, attempting to measure its spectrum and photograph its tail. After reaching perihelion on October 29, 2025, at 136 astronomical units from the Sun, just inside the orbit of Mars, it will swing past Venus on November 3, 2025, at 0.65 AU. Then it will continue outward. On December 19, 2025, 3I Atlas will pass Earth at a distance of 1.80 astronomical units, roughly 269 million kilometers. That is nearly twice the distance from Earth to the Sun. The comet will be on the opposite side of the Sun from Earth during its closest approach to our planet. It poses no threat. NASA's Planetary Defense Office confirmed this unequivocally. The trajectory calculations are precise. There is no possibility of collision. But what if there were? What if, by some catastrophic alignment, the trajectory had been different? What if 3I's Atlas were on a collision course with Earth? The implications are staggering, the consequences unimaginable. An object this massive, moving at this speed, carries kinetic energy equivalent to millions of nuclear weapons. The science does not lie. And that question leads us directly to the most terrifying scenario humanity has never faced. The nucleus of 3I Atlas is invisible. High-resolution images from the Hubble Space Telescope captured the comet in July 2025, attempting to measure the solid core beneath the glowing coma. The images revealed a profound problem. The nucleus is surrounded by a dense cloud of reflective dust particles, making it appear brighter and larger than it actually is. Scientists cannot separate the light of the nucleus from the light of the dust. The result is a range of uncertainty so wide it borders on absurdity. The diameter could be as small as 320 meters, roughly the length of 3 football fields, or as large as 5.6 kilometers, over 3 miles across. Early estimates in July 2025 suggested the nucleus might be 10 to 20 kilometers in diameter, but astronomers knew this had to be wrong. The dust was contaminating the signal. What is certain is the dust production rate. Observations indicate 3I Atlas is shedding material at a prodigious rate. If the estimated dust loss rate holds, the nucleus is likely less than 1 kilometer in diameter, similar to 2I Borisov, the previous interstellar comet. But there is a complication. NASA's Swift Observatory detected water vapor emission corresponding to an active surface area of 7.8 square kilometers. If this water is coming from the nucleus itself, the diameter would need to be approximately 4.94 kilometers. This creates a paradox. The dust loss rate suggests a small nucleus. The water vapor emission suggests a large one. The solution lies in the coma. Most scientists now believe the bulk of the water vapor is not sublimating directly from the nucleus, but from icy grains within the coma itself. The coma is not just gas. It is a swarm of microscopic ice particles lifted off the surface by other volatiles, primarily carbon dioxide. As these particles drift outward, they continue to sublimate, releasing water into space. The science is relentless. The chemical composition is shocking. The James Webb Space Telescope analyzed the coma's spectrum in July and August 2025. JWST's NIR spec instrument detected carbon dioxide, water vapor, carbon monoxide, carbonyl sulfide, and water ice. The carbon dioxide to water mixing ratio is 8.0 plus or minus 1.0, meaning there are 8 times more CO2 molecules than H2O molecules in the coma. This is one of the highest CO2 abundances ever recorded in a comet. Only one other object, Comet C2016 R2 Pan-STARRS, rivals this bizarre chemistry. Solar system comets typically show increasing CO2 to water ratios as they move farther from the Sun, because carbon dioxide sublimates at lower temperatures than water. But 3I Atlas breaks this rule. When JWST observed it at 3.5 astronomical units, deep in the outer solar system where water should barely sublimate, the comet was flooding space with CO2. There are 2 competing explanations. The first, 3I Atlas has an intrinsically CO2-rich nucleus. This would mean the comet formed near the carbon dioxide frost line in its parent star's protoplanetary disk, where CO2 ice was abundant, but water ice was scarce. Alternatively, the comet could have been bathed in intense ultraviolet radiation during its formation, converting water ice into carbon dioxide through radiolysis. The second explanation, 3I Atlas, has a thick insulating crust. Beneath this crust lies a massive reservoir of water ice, hidden and dormant. The surface layer, enriched in carbon dioxide, sublimates first, masking the true composition beneath. As the comet approaches perihelion and temperatures rise, this crust may crack, releasing torrents of water vapor. Scientists do not know which scenario is correct. The data is insufficient. The mystery persists. Then there is the nickel. On July 20, 2025, the Very Large Telescope in Chile detected atomic nickel vapor in the coma of 3I Atlas. This was not unexpected. Nickel emission has been observed in other comets, including 2I Borisov. What shocked astronomers was the absence of iron. Nickel and iron are cosmically coupled elements. They form together in stellar nucleosynthesis and exist in nearly equal abundances in most cosmic environments. When comets outgas nickel, they also outgas iron. Always. Except 3I Atlas does not. Spectroscopic observations from the VLT and Keck Observatory found no detectable iron vapor. The ratio is impossible. By August 21, 2025, 3I Atlas was emitting 4.6 grams of nickel per second. The expected iron emission should have been comparable. Instead, there was silence. The implications are disturbing. If 3I Atlas contains nickel but not iron, its parent body must have undergone chemical fractionation on a scale never seen in solar system comets. One hypothesis involves nickel tetracarbonyl, a volatile organometallic compound that could transport nickel atoms while leaving iron behind. This molecule forms through reactions between carbon monoxide and metallic nickel in low-temperature, high-pressure environments. If the comet's parent protoplanetary disk had unusual chemistry, perhaps driven by the composition of its host star, nickel-bearing organics could have been incorporated into the comet while iron remained locked in refractory grains. The process is speculative. No one has observed nickel tetracarbonyl in space, but the absence of iron demands an explanation. And there is more. On August 14, 2025, the VLT detected cyanide gas in the coma. Cyanide, or CN, is a common cometary volatile, typically released when organic molecules break apart under solar ultraviolet radiation. What is unusual is the timing. nickel emission appeared before cyanide. In most comets, CN is detected first because it is easier to spot spectroscopically. The reversed order suggests 3I Atlas has an atypical volatile distribution. Throughout late July and August, the VLT observed a rapid and steady increase in both nickel and cyanide concentrations as the comet moved from 4.4 to 2.85 astronomical units. By August 23rd, the comet was releasing 17.6 grams of cyanide per second. The emission rates are consistent with other solar system comets at similar heliocentric distances, but the nickel-to-iron ratio is not. The age remains the most profound mystery. The thick disk population of the Milky Way formed between 10 and 13 billion years ago. Stars in this region are metal poor, meaning they contain fewer heavy elements than the Sun. If 3I Atlas was ejected from a planetary system orbiting one of these ancient stars, the comet itself could be 7.6 to 14 billion years old. Some estimates push the age even higher, to 10 billion years. This is staggering. The universe is 13.8 billion years old. The solar system is 4.6 billion years old. Earth is 4.5 billion years old. Life on Earth has existed for roughly 3.5 billion years. If 3I Atlas is truly 10 to 14 billion years old, it formed in an era when the Milky Way was young, chaotic, enriched only with primordial hydrogen, helium, and trace elements forged in the first generations of stars. It is a time capsule, a frozen archive from a cosmic epoch we can barely study. Every molecule in its coma, every grain of dust in its tail, carries information about conditions in a protoplanetary disk that existed before the Sun ignited. The chemistry of that ancient system is written in the ice. The CO2 to water ratio, the presence of cyanide, the nickel emission. All of these are clues to the processes that built planets around a star that may no longer exist. That star could be dead now, exploded in a supernova, scattered into the interstellar medium. Or it could still be out there, tens of thousands of light years away, orbiting the galactic center in the thick disk, surrounded by planets we will never see. And one of those planets, billions of years ago, ejected this comet into the void. The comet drifted. For millions, perhaps billions of years, it traveled through interstellar space, a solitary iceberg in the cosmic ocean. It passed other stars. It crossed molecular clouds. It endured bombardment by cosmic rays and high-energy particles that altered its surface chemistry, darkening the ice, breaking molecular bonds, creating radicals and complex organics. And then, by pure chance, it entered the gravitational sphere of influence of the Sun. The trajectory was set. The comet was captured, drawn inward, accelerated to crushing speeds by the Sun's gravity. The ice began to boil. The coma formed. Telescopes detected it. And humanity, for the first time, could study an object older than the solar system itself. But what if this ancient visitor had arrived on a different trajectory? What if the gravitational perturbations that guided it into the inner solar system had been slightly different? What if, instead of a flyby, 3I Atlas were on a direct collision course with Earth? An object this old, this massive, this fast. What would happen? The answer is terrifying. And to understand it, we must first understand what an impact truly means. Imagine the scenario. July 1st, 2025. Atlas, telescope in Chile, detects an object moving across the sky. The computer calculates the orbit within minutes. The result is impossible. Hyperbolic trajectory. Velocity 61 kilometers per second. Origin, interstellar space. And then the confirmation no one wants to see. The projected path intersects Earth. The computer flags it as a potentially hazardous object. Alarms trigger. Within hours, every major observatory on the planet is pointing toward the same patch of sky. The calculations are run again and again. The answer does not change. 3I Atlas is coming. The warning time depends on size and distance. Atlas is designed to detect a 100-meter asteroid approximately 3 weeks before impact. A 50-meter object gets detected between 3 and 9 days out. A 20-meter asteroid, roughly the size of the Chelyabinsk meteor that exploded over Russia in 2013, would be spotted only days before collision. But 3I Atlas is not 20 meters. It is not 50 meters. Conservative estimates place the nucleus between 320 meters and 5.6 kilometers in diameter. At the lower end, the comet is larger than the Eiffel Tower. At the upper end, it dwarfs Mount Everest. An object this size can be detected at vast distances. Under favorable conditions, Atlas can spot a 100-meter asteroid at 40 million kilometers, roughly a quarter of the distance to the Sun. For 3I Atlas, assuming a diameter of 1 to 5 kilometers, detection could occur at 100 million kilometers or more. In this hypothetical scenario, the comet is detected on July 1st at a distance of 610 million kilometers, 4.1 astronomical units from the Sun. At 61 kilometers per second, it is closing the gap at over 5 million kilometers per day. Earth orbits at 1 astronomical unit, 150 million kilometers from the Sun. If 3I Atlas were targeting Earth, and if its trajectory brought it to intercept our planet at roughly 1 AU, the comet would need to travel approximately 460 million kilometers from the point of discovery. At 61 kilometers per second, that journey takes 87 days. The math is unforgiving. Detection on July 1st means impact on September 26th. Humanity has less than 3 months. The trajectory is refined. Within days of discovery, observatories worldwide, Hubble, JWST, the Very Large Telescope, Gemini, Keck, all contribute data. Every observation narrows the uncertainty. By mid-July, the impact corridor is defined. The comet will strike Earth on September 26, 2025, at approximately 14:37 UTC. The impact site is projected to be in the Atlantic Ocean, 1,200 kilometers east of the coast of Brazil. The velocity at impact will be 68 kilometers per second. The angle of entry will be approximately 45 degrees. The numbers are locked in. There is no uncertainty. The comet is coming. Public reaction is immediate. Governments convene emergency sessions. NASA's Planetary Defense Coordination Office escalates to maximum alert. The United Nations activates the International Asteroid Warning Network. Scientists calculate the impact energy. Kinetic energy is 1/2 mass times velocity squared. The mass of a comet depends on its size and density. Assume a nucleus diameter of 2 kilometers. Assume a spherical shape. The volume is 4/3 pi times the radius cubed, approximately 4.2 cubic kilometers. Comet nuclei have densities between 400 and 600 kilograms per cubic meter, far less than rock, closer to packed snow. Assume 500 kilograms per cubic meter. The total mass is 2.1 trillion kilograms. The velocity is 68 kilometers per second, 68,000 meters per second. kinetic energy equals 1/2 times 2.1 times 10 to the 12th kilograms times 68,000 meters per second squared. The result is 4.85 times 10 to the 21st joules. To translate this into comprehensible terms, 1 megaton of TNT releases 4.19 times 10 to the 15 joules. The impact energy of 3I Atlas in this scenario is equivalent to 1.16 million megatons of TNT. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, had a yield of 50 megatons. The 3I Atlas impact would release the energy of 23,200 Tsar bombers detonating simultaneously. The asteroid that killed the dinosaurs 66 million years ago, the Chicxulub impactor, released an estimated 100 million megatons. The 3I Atlas impact is roughly 1% of Chicxulub. It is not an extinction event, but it is a civilization-ending catastrophe. As August arrives, the comet becomes visible to amateur astronomers. At 2.9 astronomical units, it is still far from Earth, but the coma is growing. The water production rate reaches 40 kilograms per second. The dust tail extends across millions of kilometers. By mid-August, the comet reaches magnitude 8, visible through binoculars. By late August, it brightens to magnitude 5, on the threshold of naked eye visibility. People begin to see it. A faint smudge in the southern sky, near Sagittarius, low on the horizon after sunset. News media broadcast images. The tail is faint but unmistakable. Every night, it grows brighter. By early September, the comet dominates the sky. At 1.5 astronomical units, it shines at magnitude 2, brighter than most stars. The tail stretches 20 degrees across the sky, the width of 40 full moons. It is visible even from light-polluted cities. Children point at it. Scientists appear on television, explaining the mechanics of the impact, the scale of the destruction, the impossibility of evacuation. The Atlantic basin will be vaporized. Coastal cities, Rio de Janeiro, Buenos Aires, Lagos, Lisbon, New York, Miami, will be obliterated by tsunamis hundreds of meters high. The shock wave will circle the globe. The debris cloud will block sunlight for months. Crops will fail. Billions will starve. By mid-September, the comet is magnitude -2, brighter than Jupiter, visible even in daylight. The tail spans half the sky. The coma glows with a ghostly blue-green light from ionized cyanide and carbon. At night, it casts shadows. People stop working. They gather in public spaces, staring upward, unable to look away. Some pray, some riot, most simply wait. On September 25th, one day before impact, the comet reaches magnitude -6, 10 times brighter than Venus. It is the brightest object in the sky after the sun and moon. The tail fills the entire southern hemisphere. The nucleus, still invisible to the naked eye, glows at the center of a vast diffuse halo. Scientists track it with radar. The distance is 1.2 million kilometers, 3 times the distance to the moon. In 26 hours, it will strike. The final hours are surreal. The comet appears to hang motionless in the sky, an optical illusion caused by its direct approach. As it closes the distance to 500,000 kilometers, the coma begins to resolve into structure. Jets of gas erupt from the nucleus, visible as bright streamers against the darker background. At 100,000 kilometers, the comet subtends half a degree, the same apparent size as the full moon. But it is not solid. It is a cloud, a diffuse swarm of ice and dust held together by gravity. The true nucleus, the solid core, remains hidden within, and then it crosses the Moon's orbit. At 380,000 kilometers, humanity watches a cosmic intruder penetrate the boundary of our gravitational sphere. The Moon itself is on the opposite side of Earth, unaffected, but the symbolism is unmistakable. The comet has entered our domain. In 8 hours, it will arrive. But what happens when it does? What happens when an object moving at 68 kilometers per second, a frozen relic from a star system billions of years old, collides with the fragile crust of a living planet? The physics are clear. The consequences are unimaginable. And the question that haunts every scientist, every leader, every person watching the sky is this: could we have stopped it? The Moon's orbit defines a psychological boundary. At 380,000 kilometers from Earth, it marks the edge of humanity's immediate celestial neighborhood. When 3i Atlas crosses this line, physics shifts. Earth's gravitational field becomes dominant. The comet is no longer just falling toward the Sun. It is falling toward Earth. And Earth is pulling back. Tidal forces activate. Gravity is not uniform. The side of the comet facing Earth experiences stronger gravitational pull than the far side. This differential force stretches the nucleus along the Earth-comet axis. Simultaneously, it compresses the nucleus perpendicular to this axis. The effect is called tidal stress. The magnitude of this stress depends on 3 factors: Earth's mass, the comet's size, and the cube of the distance. As the comet approaches, the distance shrinks. The tidal force increases exponentially. The critical threshold is the Roche limit. This is the minimum distance at which a celestial body held together only by its own gravity can survive without disintegrating. Inside the Roche limit, tidal forces exceed the comet's self-gravity. The nucleus tears itself apart. For Earth, the rigid body Roche limit is approximately 18,000 kilometers above the surface. For a fluid body, one with no internal strength, the limit extends to 34,000 kilometers. Comets are neither rigid nor fluid. They are somewhere in between. Densities range from 400 to 600 kilograms per cubic meter, closer to snow than rock. Strength is minimal. Many comets are rubble piles, loose aggregates of ice and dust held together by weak gravity and minor cohesion. History provides a brutal example. In July 1992, Comet Shoemaker-Levy 9 passed within 40,000 kilometers of Jupiter's cloud tops. This was inside Jupiter's Roche limit. Tidal forces ripped the nucleus into at least 21 fragments, creating a chain of icy bodies stretching across 1.1 million kilometers of space. When astronomers discovered the comet in March 1993, it was already destroyed. The fragments orbited Jupiter for 16 months before plunging into the planet's atmosphere in July 1994. Each impact released energy equivalent to millions of megatons of TNT. The scars were visible for months. Shoemaker-Levy 9's nucleus was approximately 1.5 to 2 kilometers in diameter before breakup. Its density was estimated at 0.6 grams per cubic centimeter. The comet had negligible internal strength. It behaved as a strengthless rubble pile. When tidal stress exceeded the nucleus's self-gravity, the structure collapsed. Numerical simulations using smooth particle hydrodynamics confirmed the mechanism. The nucleus elongated, reached a critical instability threshold, and fragmented into gravitationally bound clumps. The physics is unambiguous. Now apply this to 3I Atlas. Assume a nucleus diameter of 2 kilometers, similar to Shoemaker-Levy 9. Assume a density of 500 kilograms per cubic meter, typical for comets. As 3I Atlas crosses 100,000 kilometers, tidal stress begins to build. At 50,000 kilometers, the stress is substantial. At 34,000 kilometers, Earth's fluid Roche limit, the nucleus is under extreme strain. The outer layers begin to separate. Dust and ice particles lift off the surface, not from sublimation, but from tidal forces alone. The coma expands. Jets of material erupt from stress fractures. The nucleus groans under forces it was never designed to withstand. At 20,000 kilometers, the nucleus splits. A fracture propagates through the weakest structural plane. The comet separates into 2 major fragments, each several hundred meters across. These fragments continue to fall toward Earth, but they are no longer a single object. Each fragment experiences its own tidal stress. At 15,000 kilometers, the fragments split again. Now there are 4 pieces. At 10,000 kilometers, the cascade accelerates. Each fragment breaks into smaller chunks. By the time the swarm reaches 5,000 kilometers altitude, the original nucleus has disintegrated into dozens, perhaps hundreds, of smaller bodies. The largest may be 100 to 200 meters across. The smallest are gravel, but fragmentation does not reduce the total mass. The swarm still contains 2.1 trillion kilograms of ice, rock, and dust, and it is still moving at 68 kilometers per second. The kinetic energy is unchanged. What has changed is the distribution. Instead of a single coherent nucleus, Earth now faces a cloud of impactors. The impact zone expands. The fragments are spread along the trajectory, separated by seconds or minutes of arrival time. The atmosphere must now deal with multiple hypervelocity impacts instead of one. At 2,000 kilometers altitude, the fragments enter the thermosphere. The atmosphere is still thin here, with densities around 1 trillionth that of sea level. But at 68 kilometers per second, even this tenuous gas generates catastrophic forces. Atmospheric molecules collide with the surface of each fragment at relativistic speeds. The kinetic energy of these collisions converts instantly to heat. The temperature at the stagnation point, the leading edge of each fragment, reaches 10,000 to 15,000 Kelvin. This is twice the surface temperature of the Sun. The ice does not melt. It vaporizes instantaneously. The rock does not crack. It becomes plasma. The shock wave is ferocious. Air ahead of each fragment is compressed to millions of times normal pressure. This compressed air glows white hot. The shock layer, the region between the shock wave and the fragment's surface, is a cauldron of dissociated molecules, ionized atoms, and free electrons. Oxygen molecules break apart into individual atoms. Nitrogen molecules dissociate. The gas is no longer air. It is a chemically reactive plasma. The standoff distance, the gap between the shock wave and the fragment, is roughly 14% of the fragment's radius. For a 100-meter fragment, the shock wave forms 7 meters ahead of the surface. Gas molecules travel from the shock wave to the surface in microseconds. There is no time for equilibrium. The gas is reacting, ionizing, radiating energy faster than physics can restore order. Radiation dominates. At velocities above 20 kilometers per second, radiative heating exceeds convective heating. At 68 kilometers per second, The radiation is overwhelming. The shock layer emits ultraviolet and X-ray radiation with intensity that defies comprehension. This radiation does not heat the fragment's surface through contact. It heats it through electromagnetic waves. The surface absorbs photons and heats to vaporization temperature within seconds. Material boils off in continuous streams. This process is called ablation. The fragment loses mass at a rate of kilograms per second. It is being consumed by the atmosphere. Smaller fragments do not survive. Objects less than 10 meters in diameter experience initiative, deceleration forces that exceed their compressive strength. The atmospheric drag, measured in millions of newtons, crushes the fragment. The structure collapses. The fragment explodes. This is not a chemical explosion. It is a mechanical disintegration driven by aerodynamic stress. The fragment shatters into thousands of smaller pieces, each glowing white-hot, each trailing a plume of vaporized material. The result is an aerial burst. The energy releases at altitude, typically between 20 and 40 kilometers. The shock wave propagates downward and outward. At ground level, the effect is a blast wave comparable to a nuclear detonation. But the largest fragments survive atmospheric entry. Objects 50 to 200 meters in diameter have sufficient mass and structural integrity to reach the surface. They are glowing, partially ablated, traveling at reduced but still hypersonic velocities, perhaps 20 to 30 kilometers per second. They have lost much of their ice. What remains is a rocky core superheated, surrounded by a glowing plasma sheath. These fragments will impact, and when they do, the ground will feel it. The swarm spreads across hundreds of kilometers. The first fragments arrive over the Atlantic Ocean east of Brazil. The sky ignites. A dozen fireballs, each brighter than the sun, streak across the heavens at speeds incomprehensible to human perception. Each leaves a glowing ionization trail that persists for minutes. The trails crisscross the sky like cosmic scars. People on the ground do not hear sound yet. The shock waves are still propagating. The light arrives first, and in that brief, silent moment, millions of people look up and see the sky burning. Then the impacts begin. The first fragment strikes the ocean at 25 kilometers per second. The energy release is instantaneous. The water does not splash. It vaporizes. A crater opens in the ocean. The sea floor, 4,000 meters down, is exposed for a fraction of a second. And then the walls of the crater collapse inward, and the true catastrophe begins. The first fragment strikes the Atlantic Ocean 1,200 kilometers east of Brazil at 7:14:37 UTC. The impactor is a rocky remnant, approximately 150 meters in diameter, traveling at 25 kilometers per second. The kinetic energy is calculated using the standard formula, 1/2 mass times velocity squared. Assume a density of 2,500 kilograms per cubic meter. Rocky material. Most of the ice has ablated during atmospheric entry. The volume of a 150-meter sphere is 1.77 million cubic meters. The mass is 4.4 billion kilograms. The velocity is 25,000 meters per second. The kinetic energy is 1.38 times 10 to the 18th joules. In terms of explosive yield, this is 330 megatons of TNT, 22 times more powerful than the largest nuclear weapon ever detonated. The math does not lie. The impact occurs in 3 stages: contact and compression, excavation, modification. The entire sequence lasts less than 2 minutes. Contact and compression begin, At the instant the fragment touches the ocean surface, the impactor does not penetrate slowly. At 25 kilometers per second, it moves faster than any shock wave can propagate through water. The water cannot move out of the way. It is compressed to pressures exceeding 100 gigapascals, 1 million times atmospheric pressure. At these pressures, water behaves like a solid. The molecules are crushed together. The electronic structure distorts. Chemical bonds strain to the breaking point. The temperature spikes to tens of thousands of degrees. The water does not boil. It ionizes. The ocean's surface transforms into a thin layer of plasma. The shock wave propagates. A hemispherical pressure front expands outward from the impact site at 10 kilometers per second, the speed of sound in highly compressed water. Behind the shock front, water is accelerated to enormous velocities. The sea floor, 4,000 meters below the surface, feels the shock within 0.4 seconds. The sediment layer, soft mud and sand accumulated over millions of years, is compressed and shattered. Beneath the sediment, the basaltic oceanic crust fractures. The shock wave penetrates 10 kilometers into the lithosphere. Rock that has been solid for millions of years liquefies under the extreme pressure. The entire impact region behaves as a fluid. Simultaneously, the impactor itself is destroyed. The leading edge of the fragment experiences pressures that exceed the compressive strength of rock by factors of thousands. The material does not fracture. It vaporizes. A shock wave propagates backward through the impactor at 10 kilometers per second. Within 0.06 seconds, 6 thousandths of a second, the entire 150-meter fragment has been converted into a cloud of superheated vapor and plasma. The impactor no longer exists as a solid object. It has become energy. Excavation begins. The compressed water and vaporized impactor material expand explosively. This is not a chemical explosion. This is a pressure release explosion. The plasma expands at velocities exceeding 10 kilometers per second. It pushes the surrounding water outward and downward. A transient cavity opens. The cavity grows rapidly. Within 1 second, it is 500 meters deep and 1,000 meters wide. Within 5 seconds, it reaches the seafloor. The ocean above the impact site is displaced. 4 cubic kilometers of water are ejected upward at supersonic velocities. The water does not arc gracefully. It is launched as a supersonic jet, a column of liquid moving faster than the speed of sound in air. The seafloor is exposed. For a brief moment, a cylinder of air, superheated, ionized, but recognizably empty space, extends from sea level to the ocean floor. The cavity continues to expand. The walls are not vertical. They slope outward at roughly 45 degrees. The excavation flow, the motion of material away from the impact site, is driven by the shock wave. Rock and sediment are not thrown out. They flow out. The material behaves as a fluid despite being solid. This is acoustic fluidization, a process where intense vibrations reduce the effective strength of rock to near zero. The cavity reaches maximum size at 15 seconds. The diameter is 8 kilometers. The depth is 3 kilometers, penetrating through the entire water column and 1 kilometer into the seafloor. The walls are glowing red, partially molten. The cavity is surrounded by a shock wave propagating through the ocean at supersonic speed. And above the cavity, suspended in mid-air, is a mushroom cloud of vaporized rock, water, and impactor material rising at 5 kilometers per second. Then gravity reasserts itself. Modification begins. The cavity is unstable. The walls collapse inward. Water from the surrounding ocean rushes in to fill the void. The sea floor, weakened by shock damage, slumps downward. Enormous volumes of material slide toward the center. The collapse is not uniform. It is chaotic. Different sections of the wall fail at different times. Landslides cascade into the crater. The water converges at the center. The pressure builds, and then the water rebounds. A central uplift forms. Water and liquefied rock surge upward from the crater floor. The uplift rises 2 kilometers above the original seafloor. It towers above the surrounding ocean. For a few seconds, there is a mountain of water in the middle of the Atlantic. Then it collapses. The collapse generates a second wave of excavation. Material flows outward again. The crater oscillates. Collapse, rebound, collapse, rebound. Each oscillation is weaker than the last. After 90 seconds, the motion stops. The final crater is 15 kilometers in diameter. The rim is 200 meters above the pre-impact seafloor. The floor is 1.5 kilometers below. The interior is filled with breccia, shattered rock mixed with impact melt. The crater is now submerged under 4,000 meters of water. But the water has not forgotten the violence. The tsunami begins. The collapse of the transient cavity displaces trillions of tons of water. This water must go somewhere. It moves outward in all directions. But this is not a wind-driven wave. This is an impulsive wave generated by a sudden, catastrophic displacement. The wave height at the source is 300 meters. The wavelength, the distance between wave crests, is 50 kilometers. The wave travels at 700 kilometers per hour, the speed of a commercial jet. It will reach the Brazilian coast in 90 minutes. But the first fragment is not alone. 3 seconds after the first impact, a second fragment strikes 80 kilometers to the north. This one is 100 meters in diameter. Energy yield, 100 megatons. Another crater opens. Another tsunami is born. 7 seconds later, a third fragment impacts 120 kilometers to the south. Then a fourth, then a fifth. Over the course of 40 seconds, 12 major fragments, each between 50 and 200 meters in diameter, strike the Atlantic Ocean across a 500-kilometer swath. The combined energy release is 2,500 megatons. The ocean surface is transformed into a field of overlapping craters, each generating its own tsunami, each contributing to the chaos. Smaller fragments, objects between 10 and 50 meters, airburst at altitudes between 10 and 30 kilometers. There are dozens of these. Each releases energy equivalent to the Hiroshima bomb. The airburst generates shock waves that propagate downward to the surface. The blast waves converge on the ocean. The water surface is pummeled by atmospheric overpressure. The effect is similar to a carpet bombing campaign conducted at supersonic speed. For context, consider historical impacts. The Tunguska event of June 30th, 1908, was an asteroid or comet fragment approximately 50 to 60 meters in diameter that airburst over Siberia at an altitude of 5 to 10 kilometers. The explosion flattened 2,050 square kilometers of forest. The energy yield was between 3 and 15 megatons. Eyewitnesses, 65 kilometers away, were knocked off their feet by the blast wave. Windows shattered 650 kilometers away. Seismic stations across Europe recorded the shockwave. The explosion was 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Yet Tunguska was a single airburst. The 3-eye Atlas scenario involves 12 major surface impacts and dozens of airbursts. The total energy is 100 times greater than Tunguska, but it is not Chicxulub. 66 million years ago, a 10-kilometer asteroid struck the Yucatan Peninsula in Mexico. The impact excavated a crater 200 kilometers wide and 20 kilometers deep. The energy release was approximately 10 to the 23rd joules, 100 million megatons. The impact triggered a global earthquake that shook the planet for weeks. Mega tsunamis propagated across every ocean. The atmosphere was injected with billions of tons of dust and sulfate aerosols. Sunlight was blocked for months or years. Global temperatures plummeted. Photosynthesis stopped. Food chains collapsed. 75% of all species on Earth went extinct. The dinosaurs, which had dominated terrestrial ecosystems for 165 million years, vanished. The 3-IR Atlas impact is 1% of Chicxulub. It will not cause a mass extinction. It will not end photosynthesis. It will not sterilize the planet. But it will kill billions of people. And it will collapse human civilization. Because the impacts are only the beginning. The first seconds unleash forces incomprehensible to human experience. But the first hours, the first days, those bring consequences that stretch across the globe. And the question is no longer what happens at the moment of impact. The question is what happens next. The tsunamis reach the coast first. 90 minutes after the impacts, the wave front arrives at the beaches of northeastern Brazil. The water does not arrive as a wall. It arrives as a rising. The ocean withdraws. Harbors empty. The seafloor is exposed for kilometers. Fish flop on wet sand. People walk out onto the exposed seabed, confused, curious, unaware. Then the first wave arrives. The leading wave is 150 meters high. It moves at 700 kilometers per hour, faster than a commercial jet. The wave does not break. It does not curl and crash. It is a moving wall of water that engulfs everything in its path. The wave reaches Rio de Janeiro at 8:47 UTC. The city has 90 minutes of warning. Evacuation orders are issued. Highways are gridlocked. Millions cannot escape. When the wave strikes, it penetrates 30 kilometers inland. Coastal buildings are obliterated. The wave carries debris, cars, ships, fragments of structures that act as battering rams. The destruction is absolute. The wave does not stop. It continues northward along the South American coast. Recife, Salvador, Fortaleza. Each city is struck in succession. The death toll climbs into the millions. Simultaneously, the wave propagates eastward across the Atlantic. 3 hours after the impacts, it reaches the Cape Verde Islands. 5 hours later, it strikes the western coast of Africa, Senegal, Guinea, Sierra Leone. 6 hours after impact, the wave reaches Morocco and Portugal. Lisbon is inundated. 8 hours after the impacts, waves arrive in southern Spain and France. The Mediterranean feels the surge. The tsunami is global. The wave reflects off coastlines and propagates back into the ocean. Secondary waves cross the Atlantic. The ocean oscillates for days. Ports are destroyed. Coastal infrastructure collapses. Freshwater sources are contaminated by saltwater intrusion. Hundreds of millions of people are displaced. The immediate death toll from the tsunamis alone exceeds 100 million. But the tsunamis are only the first effect. While the waves propagate across the ocean, the atmosphere is responding to the impacts. The ejecta plume, material blasted upward from the craters, rises through the stratosphere. The plume reaches altitudes of 100 kilometers or more. At these heights, the material spreads horizontally, forming a global cloud. The plume contains vaporized rock, molten droplets, solid fragments, and superheated gas. This material begins to re-enter the atmosphere. Re-entry begins 20 minutes after impact. The ejector consists of billions of molten spherules, each a few millimeters in diameter. These spherules fall through the atmosphere at terminal velocity. As they descend, they glow white-hot. The collective radiant heat from trillions of falling spherules heats the atmosphere to oven-like temperatures. The effect is comparable to turning on a global broiler. For several hours, the entire Earth is bathed in intense infrared radiation. The heat flux at ground level reaches 10 to 20 kilowatts per square meter. This is equivalent to standing a few feet from a roaring fireplace. But the heat is everywhere, inescapable. Forests ignite. The fires begin in North and South America, closest to the impact site. But as the spherules continue to fall globally, fires spread to other continents. The fires are not localized. They are continental in scale. Entire ecosystems burn. The Amazon rainforest ignites. Boreal forests in Canada and Russia burn. Grasslands in Africa and Australia catch fire. The smoke plumes rise into the stratosphere, adding soot to the already debris-laden atmosphere. The amount of soot is staggering. Estimates suggest the Chicxulub impact injected between 15 billion and 70 billion metric tons of soot into the atmosphere. The 3I Atlas impact, being 1% of Chicxulub's energy, would produce proportionally less soot, perhaps 1 to 5 billion metric tons. This soot consists of submicron particles, small enough to remain suspended in the stratosphere for months or years. Soot absorbs sunlight with extraordinary efficiency. Each particle heats the surrounding air, creating a thermal inversion that stabilizes the soot layer and prevents it from settling. Simultaneously, the impacts eject pulverized rock into the atmosphere. The fragmentation of the impactors and the target materials produces fine dust particles, most smaller than 1 micron in diameter. A 10-kilometer impactor can eject 2.5 quadrillion kilograms of dust. The 3I Atlas impact would eject roughly 25 trillion kilograms. This dust spreads globally within days. Unlike soot, dust does not absorb sunlight. It scatters and reflects it. The result is a planet enveloped in an opaque haze. The combination of soot and dust blocks sunlight. Within a week of the impacts, the amount of solar radiation reaching Earth's surface drops by 85 to 90%. The daytime sky is not bright. It is dim, twilight at noon. The sun is invisible. Temperatures plummet. Within 20 days, land surface temperatures drop by 10 to 15 degrees Celsius. Coastal regions, moderated by ocean heat capacity, cool more slowly. But continental interiors experience catastrophic cooling. Regions that were temperate become Arctic. Snow falls in the tropics. Rivers freeze. This is impact winter. Photosynthesis stops. Plants require sunlight to convert carbon dioxide and water into glucose. With sunlight reduced by 90%, photosynthesis becomes impossible for most species. Within weeks, plants begin to die. Leaves wither and fall. Crops fail. Agricultural production ceases entirely. Stored food becomes the only food, and most countries do not have sufficient reserves. Global cereal stocks represent approximately 30% of annual production. Within 4 months, those reserves are exhausted. The marine food chain collapses. Phytoplankton, microscopic photosynthetic organisms that form the base of the oceanic food web, die within weeks. These organisms produce half of Earth's oxygen and support the entire marine ecosystem. When they die, everything that depends on them dies. Zooplankton starve, fish starve, marine mammals starve. The ocean becomes a graveyard. Herbivores on land starve. Without plants, there is no food. Deer, cattle, elephants, rabbits. Every plant-eating species faces extinction. Carnivores follow. Without herbivores to hunt, predators starve. Scavengers survive longer, feeding on the corpses. But eventually, the corpses are gone. The ecosystems that took millions of years to build collapse in months. Humans are not exempt. With agriculture destroyed and food reserves depleted, famine spreads. Developed nations with larger food stockpiles survive longer than developing nations. But no nation has enough food to last a year. Governments implement rationing. Martial law is declared. Social order breaks down. Violence escalates as populations compete for dwindling resources. Epidemics follow. Sanitation systems collapse. Diseases spread unchecked. The death toll accelerates. The soot begins to settle after 6 months. The larger dust particles fall within weeks, but submicron dust and soot remain aloft for months. Precipitation helps remove particles from the atmosphere through wet deposition, but the process is slow. After a year, approximately 15% of sunlight is still being blocked. Temperatures remain depressed. Some climate models suggest it takes 5 to 10 years for the atmosphere to fully clear. During this time, ice sheets expand. Glaciers advance. 1/3 of the northern hemisphere is covered in ice. Then the greenhouse effect begins. The impacts vaporize rock and seawater, releasing enormous quantities of carbon dioxide and water vapor. The wildfires released additional carbon dioxide. These greenhouse gases do not settle. They remain in the atmosphere for decades or centuries. Once the dust and soot clear, the greenhouse gases dominate. Global temperatures rise. The temperature increase ranges from 1.5 to 7.5 degrees Celsius above pre-impact levels. The planet transitions from impact winter to impact summer. The ice sheets melt. Sea levels rise. The climate oscillates wildly. Acid rain falls for years. The shock-heated atmosphere produces nitric acid. The vaporized seawater and rock release sulfur dioxide, which reacts with water vapor to form sulfuric acid. This acid rain leaches nutrients from soil. It acidifies freshwater lakes and rivers. It poisons the remnants of ecosystems struggling to recover. The geologic record preserves evidence of this chemical assault. By the end of the first year, human population has declined by 50%. 2 billion people have died from the tsunamis, the heat pulse, the starvation, the cold, the disease. Civilization as it existed before the impact is gone. Nations have fractured. Technology has regressed. Survivors live in isolated enclaves, scavenging the ruins. This is not extinction. Humanity survives. But the world has changed. The first hours brought fire and water. The first days brought darkness and cold. The first months brought starvation and collapse. And all of this was set in motion by a visitor from interstellar space. A frozen relic from a star system billions of years old. An object that humanity could see coming for 87 days. But could humanity have stopped it? Could we have deflected it, destroyed it, saved ourselves? The answer requires understanding planetary defense, and that is where the scenario becomes even more terrifying. Planetary defense is not theoretical, it is operational. For decades, astronomers have tracked asteroids and comets that could threaten Earth. The effort is coordinated through NASA's Planetary Defense Coordination Office, established in 2016. The mission is simple: find potentially hazardous objects before they find us. The execution is anything but simple. Detection begins with telescopes. The Asteroid Terrestrial Impact Last Alert System, ATLAS, operates 4 robotic observatories located in Hawaii, Chile, and South Africa. Each unit scans the entire visible sky every 24 hours. ATLAS is designed to detect a 100-meter asteroid approximately 3 weeks before impact. A 20-meter object gets detected days before impact. The system is automated. Software identifies moving objects, calculates orbits, and flags potential threats. As of 2025, ATLAS detects tens of thousands of known asteroids per night. Most are false positives, variable stars, optical artifacts, electronic noise. Machine learning algorithms filter the noise, reducing the candidate list by 95% without losing real objects. PanSTARRS, the Panoramic Survey Telescope, and Rapid Response System operates 2 telescopes in Hawaii. PanSTARRS has a larger aperture than ATLAS, allowing it to detect fainter, more distant objects. The limiting magnitude is approximately 23, roughly 3 magnitudes fainter than ATLAS. This translates to detecting objects 4 times farther away. PanSTARRS contributed to the discovery of 2I Borisov in 2019 and has detected thousands of near-Earth objects. Simulations suggest PanSTARRS can detect Earth-impacting asteroids with sufficient warning time to mount a deflection mission. But detection is only the first step. Warning time determines what can be done. Research from the Asteroid Institute analyzed 10,000 simulated Earth-impacting asteroid orbits. The study calculated the delta VI, the change in velocity, required to deflect each asteroid so it misses Earth by at least 6,400 kilometers. The results are unambiguous. The longer the warning time, the smaller the required delta V. With 10 years of warning, most asteroids can be deflected with a relatively small velocity change, on the order of centimeters per second. With 5 years of warning, the required delta V increases. With 1 year of warning, deflection becomes extremely difficult. A NASA simulation in 2021 modeled an asteroid impact scenario with 6 months of warning time. The conclusion was stark. 6 months is not enough. The simulation assumed an asteroid 300 meters in diameter on a collision course with Earth. Participants, scientists, engineers, disaster response coordinators evaluated options. Nuclear deflection was considered. Kinetic impact emissions were evaluated. None could be implemented in time. The asteroid struck Earth in the simulation. The lesson was clear. Humanity needs 5 to 10 years of warning. Minimum. But what if the object is moving faster than any asteroid humanity has ever encountered? What if the object is interstellar? In September 2022, NASA demonstrated that asteroid deflection is possible. The Double Asteroid Redirection Test, DART, was a spacecraft built to collide with an asteroid and change its orbit. The target was Dimorphos, a 160-meter moonlet orbiting the larger asteroid Didymos. Neither object posed a threat to Earth. Dimorphos was chosen because its orbit around Didymos could be measured precisely before and after impact. This allowed scientists to quantify the deflection. DART launched on November 24, 2021. The spacecraft traveled for 10 months, covering over 11 million kilometers. On September 26, 2022, at 23:14 UTC, DART struck Dimorphos at 22,130 kilometers per hour, 6.26 kilometers per second. The spacecraft weighed 570 kilograms. The kinetic energy at impact was 11 billion joules. This is roughly the energy of 3 tons of TNT. Not much, but it was enough. The impact shortened Dimorphos's orbital period by 32 minutes. Pre-mission predictions estimated a period change of 73 seconds would constitute success. DART exceeded expectations by a factor of 26. The reason? Debris. The impact did not just transfer momentum from the spacecraft to the asteroid. It ejected massive amounts of material. Observations from the Hubble Space Telescope and ground-based telescopes revealed that DART blasted out at least 37 boulders, each over 4 meters in diameter. The largest boulders were 6.7 meters across, weighing approximately 200 tons. These boulders carried momentum in the opposite direction of the spacecraft's velocity. This recoil effect, the rocket-like thrust from the ejected debris, produced 3 times more momentum transfer than the impact itself. The mission proved kinetic impactors work. A small spacecraft can alter the orbit of a much larger asteroid. This is no longer theoretical. It is demonstrated. Planetary defense is possible. But DART had favorable conditions. The spacecraft had 10 months to reach its target. Dimorphos was 11 million kilometers from Earth at the time of impact, close enough to observe, far enough to be safe. The asteroid's velocity relative to the Sun was approximately 6 kilometers per second, typical for a near-Earth asteroid, and the mission did not have to deflect Dimorphos out of an Earth-crossing orbit. It only had to change the orbital period enough to be measurable. Success was defined in minutes, not in survival. Now consider 3I Atlas. Discovery on July 1, 2025, at 4.1 astronomical units. Impact on September 26, 2025. Warning time, 87 days. DART required 10 months just to reach Dimorphos. There is no spacecraft on the launch pad ready to intercept 3I Atlas. Building and launching a mission in 87 days is impossible. The spacecraft does not exist. The rocket does not exist. The mission plan does not exist. Even if, hypothetically, a spacecraft were ready to launch immediately on July the 1st, the trajectory would be punishing. To intercept an object moving at 61 kilometers per second, while it is still 4 astronomical units away, requires enormous delta V. The spacecraft would need to accelerate to velocities far beyond current propulsion capabilities. Chemical rockets cannot provide sufficient impulse. Ion drives are too slow. Nuclear thermal propulsion, the most powerful propulsion technology in development, might provide enough thrust, but no such spacecraft exists. Assume, impossibly, that a spacecraft reaches 3I Atlas, while the comet is still far from Earth. The deflection problem remains. A kinetic impactor works by transferring momentum. Momentum is mass times velocity. DART had a mass of 570 kilograms and an impact velocity of 6.26 kilometers per second. Momentum, 3,568 kilogram meters per second. Dimorphos had a mass of approximately 5 billion kilograms. The velocity change imparted to Dimorphos was 0.007 millimeters per second. This was enough because Dimorphos was already in a stable orbit and only needed a small nudge. 3I Atlas, on the other hand, is on a hyperbolic trajectory moving at 61 kilometers per second. To deflect it away from Earth requires changing its velocity by at least several meters per second. With a mass of 2.1 trillion kilograms, this requires an impulse of trillions of kilogram meters per second. A DART-scale spacecraft cannot deliver this impulse. Even with debris amplification, the momentum transfer is insufficient. To match the required deflection impulse would require not one spacecraft, but thousands. And there is no time to build, launch, and coordinate thousands of spacecraft. The math is brutal. Another complication: relative velocity. DART impacted Dimorphos at 6.26 kilometers per second. 3I Atlas is moving at 61 kilometers per second. If a spacecraft attempts to intercept 3I Atlas head-on, the closing velocity could exceed 70 kilometers per second. At these velocities, the impactor does not transfer momentum efficiently. It vaporizes on contact. The resulting plasma explosion imparts some momentum, but most of the energy is wasted as heat and radiation. Alternatively, a spacecraft could attempt a trailing intercept, matching the comet's velocity and impacting from behind. This maximizes momentum transfer efficiency, but it also requires the spacecraft to accelerate to 61 kilometers per second. No human-built spacecraft has ever achieved this velocity. Detection systems work. Atlas and Pan-STARRS can find objects months or years before impact. The DART mission proved kinetic impactors can deflect asteroids. But these tools assume warning time measured in years, not months. They assume objects on solar system orbits, not interstellar trajectories. They assume velocities of 10 to 20 kilometers per second, not 61. When an interstellar comet enters the inner solar system, with less than 90 days of warning, traveling faster than any deflection mission can reach, the entire planetary defense architecture becomes inadequate. Humanity is not defenseless against asteroids, but against an interstellar object like 3I Atlas. On a collision course discovered with 3 months of warning, there is no defense. The question is not whether we could stop it. The question is whether we could do anything at all. And that forces us to consider options humanity has never seriously evaluated. Options that exist only in theory, untested, unproven, and utterly desperate. Nuclear weapons are the last option. When kinetic impactors fail, when time runs out, when the object is too massive or too fast, humanity considers detonation. This is not science fiction. Nuclear deflection has been studied for decades. The physics are understood. The technology exists. But the execution is nightmare. The concept is straightforward. Detonate a nuclear device near the asteroid's surface. The explosion vaporizes surface material. The vaporized material expands explosively, acting as a rocket thrust. This impulse changes the asteroid's velocity. If executed years before impact, even a small velocity change deflects the object away from Earth. The advantage over kinetic impactors is energy density. A nuclear warhead delivers millions of times more energy than a spacecraft collision. A single warhead can impart momentum equivalent to thousands of kinetic impactors. But 3I Atlas presents insurmountable challenges. First, delivery. Nuclear warheads are designed for terrestrial targets, not interstellar comets. The warhead must be attached to a spacecraft capable of intercepting an object moving at 61 kilometers per second. No such spacecraft exists. Building one requires years. Humanity has 87 days. Second, timing. Nuclear deflection requires detonation when the object is far from Earth. The velocity change accumulates over time. Detonating close to Earth produces insufficient deflection. But 3I Atlas is discovered at 4.1 astronomical units and closing rapidly. By the time any mission could reach it, the comet would be too close for deflection to matter. Third, fragmentation. Comets are weak, porous bodies. A nuclear detonation might not deflect 3I Atlas. It might shatter it. This transforms one large impactor into dozens of smaller fragments, all still on collision course. The result, instead of a single catastrophic impact, Earth faces a shotgun blast of hypervelocity projectiles. The total kinetic energy is unchanged. The devastation spreads across a wider area. Gravity tractors are useless here. The concept involves parking a spacecraft near an asteroid and using the spacecraft's gravitational field to slowly pull the asteroid off course. This method works for objects detected decades in advance. It requires years of continuous thrust. 3I Atlas allows 87 days. The gravitational deflection would be measured in micrometers. Worthless. Laser ablation is theoretical. High-powered lasers vaporize surface material, creating thrust. But the lasers must be space-based, positioned near the target. No such system exists. Development would require decades and trillions of dollars. Mass drivers, solar sails, ion beam deflection, all require warning times measured in years or decades. None are relevant to an interstellar object discovered 3 months before impact. The brutal truth: if 3I Atlas were on a collision course with Earth, humanity could do nothing. Absolutely nothing. Detection systems would spot the comet. Astronomers would calculate the trajectory. Governments would convene. Scientists would propose solutions. And all of them would fail. The comet would strike. Billions would die. Civilization would collapse. And humanity would watch it happen, helpless, for 87 days. But why? What makes interstellar objects uniquely undeflectable? The answer lies in physics, in velocity, in the unforgiving mathematics of orbital mechanics. And that reveals the most terrifying aspect of 3I Atlas. Velocity is everything. In orbital mechanics, delta V determines what is possible and what is not. Delta V is the change in velocity required to accomplish a maneuver. To deflect an asteroid, spacecraft must reach it, match its velocity, and impart momentum. Every step requires delta V. And delta V is limited by propulsion technology. Near-Earth asteroids move at 10 to 30 kilometers per second. These are typical solar system velocities. Spacecraft can reach these objects with existing chemical rockets. DART intercepted Dimorphos at 626 kilometers per second. The entire mission required approximately 5 kilometers per second of delta V. This is achievable. 3I Atlas moves at 61 kilometers per second. This is twice the velocity of Oumuamua, the previous record holder. To intercept 3I Atlas requires matching this velocity. A spacecraft launched from Earth starts at zero velocity in the interstellar reference frame. It must accelerate to 61 kilometers per second just to catch up. No propulsion system can deliver this delta V. Chemical rockets max out at 10 kilometers per second. Ion drives can theoretically achieve higher velocities, but acceleration is slow. Years to reach target speed. nuclear thermal propulsion could provide 20 to 30 kilometers per second. Still insufficient. Nuclear pulse propulsion, detonating nuclear bombs behind the spacecraft, might reach 100 kilometers per second, but the technology is untested and would take decades to develop. Even if a spacecraft reached 3I Atlas, the deflection problem remains. Deflecting a 2-kilometer, 2 trillion kilogram object moving at 61 kilometers per second requires enormous momentum transfer. The required impulse is proportional to mass times velocity change. To deflect 3I Atlas by even 1 meter per second, barely enough to miss Earth, requires an impulse of 2 trillion Newton seconds. DART delivered 3,568 Newton seconds. The 3I Atlas deflection requires 560 million DART missions. The impact velocity compounds the problem. A head-on intercept produces closing speeds of 70 kilometers per second or more. At these velocities, the impactor vaporizes instantly. Most kinetic energy converts to heat, not momentum transfer. Efficiency plummets. A trailing intercept maximizes efficiency, but requires the spacecraft to accelerate to interstellar velocities. Impossible with current technology. Interstellar objects are fundamentally different. They are not bound to the sun. Their trajectories are hyperbolic. They pass through the solar system once and vanish forever. There is no second chance. There is no time to prepare. By the time telescopes detect them, they are already inbound. By the time trajectories are calculated, they are already close. By the time missions are proposed, it is already too late. Humanity's planetary defense infrastructure assumes solar system objects, asteroids with predictable orbits, years of warning time, velocities measured in tens of kilometers per second. 3I Atlas breaks every assumption. It is an intruder from another star system. It appeared without warning, and it moves faster than anything humanity can chase. The math is unforgiving. Physics does not negotiate. If an interstellar comet targets Earth, we cannot stop it. Not with current technology. Not with decades of warning. Not at all. But here is the revelation. The truth that changes everything. 3I Atlas is not targeting Earth. The trajectory is clear. 3I Atlas will not hit Earth. It never was going to. The calculations are unambiguous. The comet's path carries it through the inner solar system on a trajectory that misses Earth by 270 million kilometers. Perihelion occurred on October 29, 2025. The comet passed 1.36 astronomical units from the Sun, just inside the orbit of Mars. It swung past Mars on October 3rd at a distance of 0.19 AU. ESA's Mars Express and ExoMars observed the flyby. On November 3rd, it will pass Venus at 0.65 AU, and on December 19th, 2025, 3I Atlas will make its closest approach to Earth, 1.80 astronomical units, that is 269 million kilometers away, nearly twice the distance from Earth to the Sun. The comet will be on the opposite side of the Sun during closest approach. Earth and 3I Atlas will be separated by the Sun's entire diameter, plus 1.8 AU of empty space. There is zero probability of collision. NASA's Planetary Defense Office confirmed this immediately after discovery. The object poses no threat. The entire catastrophic scenario, the impacts, the tsunamis, the fires, the impact winter, the collapse of civilization, is hypothetical. It never was real. It was a thought experiment. an exploration of what would happen if the trajectory were different. If the gravitational perturbations that guided 3I Atlas into the solar system had been slightly altered. If the comet had arrived a few months earlier or later. If the orbital plane had been tilted by a few degrees. But it was not. 3I Atlas is a visitor, not an executioner. It appeared from interstellar space, raced through the inner solar system, and will depart forever. Humanity is safe. The hypothetical impact will never occur. Billions will not die. Civilization will not collapse. The real 3I Atlas is a scientific treasure, an emissary from another star system, a frozen archive of chemistry from a planetary disk that formed billions of years before the Sun. Every observation, every spectrum, every image adds to our understanding of how planetary systems form across the galaxy. The relief is immense, but the lesson is clear. Someday, an object like 3I Atlas will be on a collision course. Someday, the calculations will show impact probability of 100%. Someday, humanity will face the scenario explored in the previous blocks. And when that day comes, we must be ready, because right now, we are not. 3I Atlas is teaching us. Telescopes across the globe are watching it. Hubble captured images of the nucleus and coma. JWST analyzed the chemical composition. The VLT detected nickel and cyanide emissions. NASA's Swift Observatory measured water production rates. Every dataset reveals something new. The comet's age is staggering, between 7.6 and 14 billion years old, possibly older than the solar system itself. This makes 3I Atlas a messenger from the early Milky Way. Its chemistry reflects conditions in a protoplanetary disk that existed when the galaxy was young. The high CO2 to water ratio suggests formation near the carbon dioxide frost line or exposure to intense radiation. The nickel emission without corresponding iron challenges our understanding of comet chemistry. The cyanide detected in the coma provides clues about organic molecule formation in other star systems. Spacecraft may sample the comet's tail. NASA's Europa Clipper and ESA's Hera mission could pass through the ion tail of 3I Atlas in October and November 2025. If this occurs, instruments on board will analyze particles directly. This would provide the first in situ measurements of interstellar cometary material. Future missions are being considered. An interstellar comet explorer, IC concept, proposes launching a spacecraft to intercept the next interstellar visitor. The mission would require a fast response architecture, spacecraft pre-positioned in orbit, ready to launch within weeks of detection. Propulsion would need to be nuclear or solar sail-based to achieve the necessary delta V. Such a mission could answer fundamental questions about the chemistry, structure, and origin of interstellar objects. 3I Atlas also reveals the frequency of interstellar visitors. 3 confirmed objects in 8 years. Oumuamua in 2017, 2I Borisov in 2019, and 3I Atlas in 2025. Statistical models suggest one interstellar object passes through the inner solar system every year. Most go undetected. They are too faint, too fast, or arrive from directions not monitored by telescopes. Improved detection systems like the Vera Rubin Observatory, scheduled to begin operations in 2025, will dramatically increase discovery rates. The galaxy is full of these wanderers. Comets ejected from planetary systems during formation. planetesimals scattered by gravitational interactions, debris from stellar collisions. Every star system likely contributes millions or billions of objects to interstellar space. Over billions of years, these objects fill the galaxy. Occasionally, one passes through our solar system. When it does, we glimpse the chemistry of distant worlds. 3i Atlas is not dangerous, but it is profound. It represents something larger than itself, a connection to the cosmos beyond the sun, a reminder that we are not isolated. The universe is vast, ancient, and filled with relics from epochs we can barely imagine. We are children of the cosmos. Every atom in our bodies was forged in stars. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all created in nuclear furnaces and scattered across space by supernovae. We are made of stardust. This is not metaphor. This is physics. 3i Atlas is stardust from another system. Its atoms were forged in a star that may no longer exist. They condensed into ice and rock in a protoplanetary disk billions of years ago. They orbited that star for millions or billions of years until gravitational perturbations ejected them into the void. And they drifted through the darkness between stars, across tens of thousands of light years, for billions of years, until July 2025, when this ancient traveler crossed paths with the sun. For a brief moment, a few months in the life of an object billions of years old, 3i Atlas passed through our solar system. Humanity detected it, studied it, marveled at it, and learned from it. The comet will leave soon, by early 2020. It will cross beyond the orbit of Jupiter. By 2027, it will exit the solar system entirely. It will return to interstellar space. It will drift for millions or billions more years. Perhaps it will encounter another star. Perhaps intelligent beings there will detect it, study it, wonder where it came from. Perhaps they will realize it passed through our solar system. Perhaps they will wonder if anyone here noticed. We noticed. We saw it. We calculated its trajectory. We imagined what would happen if it struck Earth. We realized we could not stop it, and that realization should terrify us, because someday the threat will be real. Someday, an interstellar object will target Earth. And when that day comes, humanity must have answers. We are not ready. Our detection systems work. Our deflection technology functions for solar system objects. But against an interstellar intruder moving at 60 kilometers per second, with 3 months of warning, we are helpless. This is unacceptable. We must build better propulsion. We must develop faster response mission architectures. We must expand detection networks to find these objects earlier. Survival demands it. But 3i Atlas also teaches us wonder. It reminds us that the universe is vast and ancient, that chemistry is universal, that the same processes forming planets around the sun occurred around distant stars billions of years ago, that we are not alone in the cosmos, not because of alien civilizations, but because the laws of physics operate everywhere. Carbon, oxygen, nitrogen, water, organic molecules, these exist throughout the galaxy. Life's ingredients are cosmic. 3i Atlas carried those ingredients across interstellar space, a frozen library from another world, a time capsule from the early Milky Way, a messenger from a star we will never see. For a few months in 2025, that messenger visited us. We learned its secrets. We calculated its age. We measured its chemistry. We imagined its origin, and we watched as it continued its eternal journey into the void. We are the universe trying to understand itself. Every observation, every measurement, every discovery is an act of cosmic self-awareness. 3i Atlas does not know. It is being studied. It does not know. It is ancient. It does not know. It carries secrets from a star system billions of years old. But we know. And that knowledge transforms a frozen rock into a revelation. Brace yourselves.